Yeah. Hello, good evening, everyone who are in Sri Lanka, and also good morning, Shahsha. And so at the University of Morato, we had a initiative to introduce quantum computing and the related concepts to undergraduates and graduate students. So as that initiative, today we have uh, not a basically workshop, but it a kind of introduction plus some hands-on work on the quantum machine learning. And so today our invited speaker is Ms. Shahsha Joshi. So let me briefly introduce Ms. Shahsha. Shahsha Joshi is a staff scientist in quantum computing at CMC Microsystems Canada. She holds a Master of Science degree in Computer Science with a focus on quantum computing from the University of Victoria and a Bachelor of Engineering in Computer Science Engineering from Punjab University, Chandigarh, India. Shasha is an NSER Create Quantum BC graduate and an IBM Qiskit advocate. And actually, I'm also from University of Victoria, so it's a great pleasure to invite you and had a session. And so I would like to invite you to the session. Thank you very much for accepting our invitation as well.
Thank you so much for the great introduction. And also, thank you so much to you and Kitman for inviting me for this event. It's always a pleasure to teach quantum computing, especially quantum machine learning, to everyone. Let me quickly share my screen. Um, awesome. Perfect. So, hi everyone. I'm Sasha, like Professor introduced me to you. I'll be giving an introduction to a very basic primer to quantum machine learning. If you are new to the concept of quantum computing or new to how the quantum counterpart of machine learning is being done or how the concepts are being implemented, you're at the right place, I would say. A little about me. As Professor mentioned, I am a staff scientist in quantum computing at CMC Microsystems Canada. CMC Microsystems is a non-for-profit organization, and since our inception, we've been working to build advanced and deep tech technology in Canada. We're always open to collaborating with other people, and especially academics and small to medium scale enterprises. And we can consult you on any quantum computing help, any project that you're working on. You just have to get in touch with me or my team at CMC Microsystems, and we'll definitely help you on your project. Along with being a staff scientist, or due to being a staff scientist, my day-to-day life looks like doing research in quantum machine learning and also some amount of quantum software development. I have a master's degree in computer science, so I come from a very software background. Hence, I work in more quantum software applications and on the quantum software side of the things. And as Professor mentioned, I am also from University of Victoria. I did my master's from University of Victoria. I am actively involved in open source development, and I really love educating and mentoring students. So if you need any help on anything, any project, any guidance, or any help for applying for like graduate applications or undergrad applications, or even PhD applications, you can reach out to me anytime. So over the next few minutes, I would be introducing you to machine learning, followed by quantum machine learning, the types of quantum machine learning algorithms that we commonly see in the field, and I'll also discuss certain applications of quantum machine learning. So that is up to you and as to how you want to explore that. And based on those applications, I also have a hands-on coding session. So the hands-on coding session would take a little longer, but I will try to complete my slides in the next 15 to 20 minutes. And I would really love if you come up and ask questions in the middle of my presentation. I'm completely fine with that because that helps me maintain my momentum as well. So if you have a question, do not hesitate to raise your hands or pop it in the chat channel. I would keep my chat box open. Awesome. So let's get started. I know you all are from grad studies and undergrad studies, and you may or may not have a background in machine learning. But if I have to introduce machine learning to you, it would be starting with the concept of traditional learning. That is how a person traditionally learns anything. So when you're trying to learn anything, or let's assume you have a baby and you're trying to teach a baby something. So you would always give that baby some kind of rules and data and would expect some outcome or an answer from that baby. So let us assume you're teaching a baby what an apple is, and you show the image or you show an apple to the baby, and you would always point out the very obvious things like the apple is bit circular in shape, it is red in color. So you're providing the baby, which is a learning material, which is a machine that tries to learn, you're providing the rules, such as the apple is always red and the apple is always circular. And you're also providing it with some data, that is, you're showing images of various apples that can be out there. And you're teaching the baby with these rules and data and expecting some answers from it. So whenever you pick up a new apple and show it to the baby would be very quick on its steps to point out that that particular thing in your hand is an apple. However, things change a little when you are trying to make a machine learn something and not just a human machine. In case of machine learning, instead of providing rules and data, you provide answers and data. That is, you have some apples with you and you point out that all of these are apples. However, you do not teach the machine any kind of a rule, but you expect the machine to learn all these rules by itself and point it out to them and point them out to you. So you would provide, let's say, images of the apples that you have and the answers stating that the images you provide are in fact apples, and the machine would point out rules such as an apple is red, an apple may be a shade of green as well, or an apple may be circular, or if the apple is too big or too small, it may be an oval shape or a disfigured shape as well. But it is all up to the machine to learn these rules. All you have to provide is images of apples and the fact that these are apples. You just need to state that these are apples. And this is how the machine would take in the inputs, the answers and data from you, try to learn from the answers and data by itself, and provide you with the rules. Now, machine learning can be of various types. Most prominently, there are three different categories in machine learning. Unsupervised learning, which is based on input only. That is, you're only giving the machine some data. There are no answers or there are no labels to that data, and you expect the machine to figure out the rules and figure out the correlations between that data itself. The second is supervised learning. This is the most common way of making a machine learn. And in supervised learning, you provide the machine with the answers and the data. That is, you provide the labels to the data. That is, if you're providing images, you also label those images stating that this is an apple or maybe this is an orange. You provide both the inputs and then you expect the machine to learn from both the inputs and provide you with the answer. And the third type of machine learning is reinforcement learning. And such kind of a learning is based on decision making. So you expect the machine to make a decision. If it makes the right decision, you reward it. But if it makes the wrong decision, you penalize it. So every time the machine makes the correct decision and knows that it's being rewarded, it would start biasing itself towards making the correct decision in future tests. Now, unsupervised learning, supervised learning, and reinforcement learning, they have their own categories as well, or types of algorithms that exist under them. During the course of this presentation and also during hands-on coding, I would be commonly talking about classification, supervised learning, classification. So in supervised learning, classification refers to the fact that you are given two or more different classes of data, and you expect the model to classify that data into its classes or distinguish between those data types. So model helps in the classification of unseen data. You would train it on some data that you have, and then you would expect the model to perform the same classification on a test set or an unseen data. Now, most commonly, let's say in this GIF, you're given two different classes of data, the blue class and the red class. The model would construct or build a linear line or a linear hyperplane separating these two data types. So if you plot the data types into a 2D axis, onto a 2D axis, you would see that the model that you train for supervised classification purposes, it would draw a straight line distinguishing the two different classes of data. And most commonly, if I have to give a mathematical expression of how supervised learning, especially classification, works, is that you provide the machine with some labeled data. And by labeled, it means you have both the data and the answers that you provide to the machine. So X here refers to the data that you have and all the features of that data. And Y here refers to the labels that you have, something that labels the data, that it's an apple, it's an orange, or maybe the Titanic drowns, or maybe every person in the Titanic drowns, or maybe they are saved, or something like that. And the supervised model would learn the function such that it can classify or generalize any unseen data that you provide after it. So you would train the model on this data, and then you would expect the function that it builds to generalize over unseen data. And how the function would generalize it, it would take in the X, which is the data and the features, and it would start giving you the outputs or the results Y for any new unseen data that you provide. Now, we were talking about classification, and we saw an image classifying two data sets into with the help of a linear boundary or a linear line separating those two data sets. But what happens if, let's say, the data is nonlinear? And when I say nonlinear, I mean data is complicated that you cannot draw a straight line or a linear hyperplane distinguishing between the classes of data that you provide. And I would say that the fix is high dimensional feature mapping, but let me tell you how this data looks like. So in real world data, like in real life, the data that you see would not always be so distinguished that you can draw a straight line from it. It would be very complex. You may see some data that is along this hyperbolic curve in the blue class, and some data in this red hyperbolic curve in this red class. However, if you try to draw a straight line distinguishing between these two data classes, you would be unsuccessful in doing that, because there is no possibility that you can simply use a linear line or a linear hyperplane to distinguish these two classes, at least in 2 dimensions, that is, if they are plotted on the XY axis. But what you would need is, in fact, the decision boundary or the classification needs to be done in a hyperbolic curve as well. That is, you would need to have a hyperbolic curve differentiating between these two classes rather than a linear line. And how you reach to this hyperbolic curve is you take the data that you have, let's say in a 2-dimensional space, or the dimensional space is defined by the number of features your data has. So you would take it from the n-dimensional space of features, and you would try to bring that data to a higher dimensional space. Now, once you bring that data to a higher dimensional space, the data becomes very easy to distinguish or classify with the help of a linear line. And this is very nicely shown in this small GIF here, although I cannot control the speed of this GIF. But if you wait and see, you would be able to recognize that the classification starts with data that are two concentric circles, red and blue. And there's no way you can draw a straight line unless you bring this data or you take this data to a higher dimensional space. And then you can see the red being very nicely distinguished from the blue class, and you can draw a straight line right through the diagonal, or right as a diagonal in the square. So this is just a visualization of how you can take your data from n feature space and plot it onto a higher dimensional space so that you can classify the two data classes. Now, how you can commonly do that? There are multiple models that help you take data from a low dimensional space to a higher dimensional space, and that help with the classification of data sets. One of the models is a support vector machine. So a support vector machine, like I said, would take your data from an n feature dimensional space to a higher dimensional space, such that you can draw a straight line through the data, distinguishing all the classes. And how it does that is it uses kernels. Kernels are just functions that help you plot your not plot, I would say, but help you take the data from a low dimensional space to a higher dimensional space. And these kernels, the space that you eventually take your data to is called the feature space. So you take your features from an n-dimensional space, which is a lower dimensional space, to a higher dimensional feature space. It's called the feature space because that is where the features exist now. And you can very clearly see in this image that if you have two data set of two different classes where it is impossible to draw a straight line through the two different classes, the orange and the green class, since they are not linearly separable in the feature space, you can go ahead and plot them on a higher dimensional space or in an enlarged feature space or a higher dimensional feature space. And then you can simply draw a curved line. By a curved line, I mean you can simply draw a hyperplane, a linear hyperplane through these two different classes and try to classify them in different data classes. And once you collapse all the data points onto a 2D plane again, or if you try to look at this enlarged feature space from, let's say, the top view along with the hyperplane that you drew, you'll see that the hyperplane looks something like this, a curved circle. So this curved circle may be non-linear in the original feature space, but in the higher dimensional feature space, this curved circle or this circle would appear as a linear hyperplane. So as a summarization, what support vector machine does is it takes nonlinear data that cannot be separated by a linear line to a higher dimensional space or a feature space, such that you can draw a linear hyperplane through the two different data sets or two different classes. And if you view this enlarged feature space from above, you'll see that that hyperplane or that linear hyperplane looks something like a circle that differentiates or classifies these two different classes. There are other ways to perform such high dimensional feature mapping to classify two different classes or multiple different classes. And another common way is to use classical neural networks. So if you have ever seen neural networks, you would know that there is an input layer that takes your data, and then you have certain hidden layers that modify your data. And at the end, what you would get is an output layer, which consists of the answer that you're expecting from the neural network. Now, this neural network, these hidden layers particularly, they play this role of higher dimensional feature mapping. So every new hidden layer that you add to your neural network would try to map the data from its n feature space to a higher dimensional feature space. So the more neurons you add or the more hidden layers you add, the greater the dimension you're taking your data to. And this is what helps neural networks to classify the data as well. So this is an image of how it would look like when you're adding multiple different hidden layers. So let's say you start with only one input layer and one hidden layer. You can see that this type of a neural network would try to classify the two data classes, the blue and the red, which are not linearly separable in a two-dimensional space, with just a linear line, because you just have one hidden layer, or maybe it's slightly unlinear line, but it would still not be able to classify it with a good accuracy. So the more number of hidden layers you add, the more the data is being mapped to a higher dimensional space. And once you take it to a higher dimensional space, you can see that the blue class is very linearly separable from the red class. You can simply draw a straight line through these in between these two classes, such that the blue class is perfectly distinguished from the red class. And this happens because you're taking the data to a higher dimensional space with the help of these hidden layers. So each hidden layer corresponds to increase in the dimension. And once you increase the dimension, you can very easily linearly classify your data. Now, how does this all tie up with quantum machine learning? Now, let me first introduce you to quantum machine learning in the sense how it is different or similar to traditional and machine learning or classical machine learning. And then let me tell you how it helps you in doing this high dimensional feature mapping for classification purposes. So quantum machine learning, it is simply a field that lies at the intersection of quantum information and machine learning. So you're using quantum mechanical properties such as superposition, entanglement, or interference in order to do some machine learning work. If you look at this diagram right here, you would see that quantum machine learning or a quantum machine learning model is very similar, or in fact, the same as a machine learning model, where you provide answers and data to your machine and try to make it learn such that it gives out rules. So the only difference between machine learning, classical machine learning, and quantum machine learning is that quantum machine learning leverages these quantum mechanical properties like superposition, entanglement, and interference to provide you with better insights or insights into your data, or to better provide you with techniques that help you classify or regress your data. So what's the benefit of having quantum machine learning? Of course, these three quantum mechanical properties are great, but these three properties help you to map data naturally into a high dimensional space. So quantum machine learning is already, or quantum computing is already a higher dimensional space, or it already naturally has a higher dimensional space. So whenever you take your data and you map it onto a quantum state, that is, you're taking, let's say, 0 and mapping onto get 0, you're already naturally doing this high dimensional feature mapping. So anything that you plot onto this block sphere, or anything you embed onto a quantum circuit, would be in a higher dimensional space. So once we have this natural higher dimensional space, mapping data becomes easy. And once we have the higher dimensional mapping, we can very easily, or with all these benefits of having a natural high dimensional space, we can classify the data with a linear decision boundary with techniques like support vector machines or neural networks. So explaining more onto this, you would have we have quantum computers that take a classical data, let's say X, and maps it onto a quantum state, and that quantum state is given by phi X or psi X. And formally, this thing, this mapping onto from a classical space to a quantum space is known as a feature map. So simply embedding anything onto a quantum circuit is using a particular feature map, or that particular embedding, to take classical data X to psi of x, get psi of x. Formally, if I have to, for statement purposes, if I have to give a definition, a quantum feature map, something that takes classical data to and maps it onto a quantum state, is given by this equation right here. It takes x from the classical dimensional space to rho of x, and this rho of x is given as a density matrix. So if you don't want to remember this, it's completely fine. You can remember this small equation for simplicity purposes, that anything you take from classical space and map it onto a quantum space is represented as a higher dimensional quantum state given by this ket of psi of x. Now, the obvious question becomes is what kind of feature maps then exist that can help us take this classical data to a quantum space? And the answer is you have a lot of different data embeddings out there. The data embeddings are nothing but feature maps that help you take classical data, plot it onto a quantum circuit, and have that data being represented on a quantum space. So what different kinds of data embedding exists? I'm only going to give you few examples here, but there are a lot more data encoding or data embedding methods out there. Very simple one is the basis encoding. And this basis encoding takes your classical data X and plots it in onto different qubits. So let's say you have number 2 and you wish to plot or take number 2 from a classical dimensional space to a quantum space by embedding this data onto different qubits. And how you would embed these this number 2 onto these qubits is you would change it to its binary form, which is 1, 0, and then you would plot 1, 0 on the quantum circuit. And how that quantum circuit looks like is qubit 0 would be assigned the value 0, and qubit 1 would be assigned the value 1 with the help of C0 gates, and you would have the embedding 0, 1 on a quantum space. However, you're all here, you're naturally taking this two number or a classical number to a higher dimensional space by simply plotting it on a quantum circuit or by simply taking it to a quantum feature space. The second type of encoding is angle encoding. So you must have seen different gates being utilized on quantum circuits, and some of those gates also have this theta value assigned to them. That is how much rotation you wish to see on the Bloch sphere, and that theta value, if you replace that theta value by the data that you have in hand, the classical data, and you use that classical data as this theta value inside these gates, such encoding is called angle encoding. Amplitude encoding, on the other hand, is when you describe the quantum state as a linear combination of how many states it has. You would see an amplitude assigned to each possible state. If you try to encode your classical data as these amplitudes, that type of encoding or embedding would be called amplitude encoding. And there are other difficult, or I would say other more complex feature maps out there. One very common example is a ZZ feature map. If you have worked even a little bit with Qiskit or any other software development kit out there for quantum, you would see that there is a ZZ feature map. It has this complex equation, but I'm not going to dive deeper into it. But it also is a type of data embedding. So it takes classical data and plots it onto a quantum space. I would pause here for a few minutes and would ask if anyone has any questions. Okay, I do see something. Okay, that's a very good question. So Kitman asks, is there a motivation for using a qubit to capture higher dimensional embeddings on our data set in opposition to using dimensionality reduction techniques on the data set? That is a very nice question. And the answer is there is a difference. First of all, there is a difference between embedding everything on a higher dimensional space and second, using a dimensionality reduction technique. So in a dimensionality reduction technique like PCA, what you do is you take all the features of your data set and try to reduce the number of features that you actually take into consideration. So it may not show you the effects for a smaller data set, but when you have data sets that are extremely essential, that have features that are extremely essential and you cannot miss out on any feature out there, you need to have a technique where you use all those features. And sometimes those features can be, like I said, impossible to classify linearly. So you will have to map them onto a higher dimensional space to draw that linear boundary. A very common example would be medical imaging. I've worked in medical imaging, classification of medical imaging for some while. And in these medical data sets, which consists of, let's say, CT scans, MRI scans, every piece of information or every feature in those images is an essential information. Using dimensionality reduction techniques on them reduces the context that we have on those images. So either you're losing out on certain pixels or you're losing out on certain intensity differences or brightness differences in the color of those images. And even a small thing that you reduce using those dimensionality reduction techniques may cause you to incorrectly classify those images. So if you're trying to detect a tumor may be simply present on one of those pixels or maybe half of those pixels. And by dimensionality reduction techniques, you're losing context on a lot of different things around that pixel or maybe that pixel itself. And so in cases like these, when you have to use all the features present in those images, you may want to use higher dimensionality mapping so that you can easily classify those images using the linear decision boundary. I hope that answers your question. If anyone has any more questions, feel free to ask. Absolutely. Can I explain what entanglement is? So, entanglement is this inherent property of quantum bits where, in mathematical terms, they are linearly entangled or linearly, I would not use this word combined, but I would say combined or connected to each other such that two qubits or two bits of information may behave as just one. So when you try to look at one of the qubit that you have in hand that is entangled to some other qubit, you're basically collapsing the quantum properties of the entire set. So you can always think of entanglement as coupling two different qubits, not coupling, but connecting two different qubits such that they cannot be individually recognized from that set. They would from now on be visible as a set of two qubits only, and you cannot get their individual properties out from that set. This is a very simple explanation of what entanglement would mean. And this is how I actually understood what entanglement is. In mathematical terms, when you have two qubits entangled with each other, they have this linear representation. Let's say amplitude with ket 1, 0 plus amplitude with ket 0, 1. These two qubits now only exist as a single system. It is impossible to get separate values or individual values of those two qubits. You cannot linearly decompose the equation of ket 1, 0 plus 0, 1 into its different forms. And by different forms, I mean what different values can each qubit take. You cannot decompose them. Again, I hope that answers your question. Okay, we have another question. For one data point to take an embedding, do you have to do all three? Okay, that's a good question. So it depends on what your data looks like. So if you're talking about basis encoding, if let's say I'm trying to encode 2, 2 in its binary would be 1, 0. So I would only need to have 2 qubits to embed that number 2. But if I have, let's say, number 4 in binary is given as 1, 0, 0. So I have 3 binary units to encode, that is 1, 0, 0. So I would use 3 qubits to encode 4 onto the circuit. Another question, can I know a bit more on angle encoding? Do we directly use X in the unitary operations? That is absolutely correct. We directly use X in the unitary operations. There could be some pre-processing, but that pre-processing is limited to normalizing your data set or making sure that the data exists between certain angle limits, that is from 0 to pi or minus pi to pi, whatever the unitary gate accepts. But you can directly use that data. And this is something that we would also see in the hands-on coding. You would directly use that data and encode it onto a unitary gate as its angle. Awesome. I do not see any more questions, but if you have more questions, feel free to ask them. Okay, there's another one. If we have a limited number of qubits, which method can be used? That is an amazing question because I would say it is an active field of research. Data embedding is one of the heaviest subtasks in quantum or quantum machine learning. So the type of data embedding you use defines how many qubit requirements you have and how much complexity you would see in your quantum machine learning or quantum computing algorithm. So if you use basis encoding, you can see that the basis encoding, you would see that basis encoding has a fixed number of qubits that you would require. So if you're embedding 2, you would have 2 qubits. If you're embedding 4, 4 in its binary would have 3 units, so you would have 3 qubits. Angle encoding takes a little less. Uh, it depends on how many data features you have. So if you have to encode 2, you with the help of angle encoding, you can only use 1 qubit, encode 2 as the theta in that particular UX gate, and you have completed your angle encoding. Similarly, for 4, you would only need 1 qubit. So you can very visibly see the difference in the type of, in the number of qubits you would require for basis encoding and angle encoding. The best encoding right now is the amplitude encoding. It is a little complex to do. You have to normalize your data set and then make sure you're implementing the correct gates such that your data appears as the amplitude value in the quantum state. But there is an upper limit on how many qubits you can use for amplitude encoding as well. I would have to refer some paper for it. I do not have it on top of my head, but the type of data encoding you choose fixes the number of qubits you would require, and it is an active area of research as to how we can use the best data encoding or data embedding to use the least number of qubits possible. Okay, any more questions? Awesome. So if you are clear with the types of data embedding, let's jump on to see what types of QML algorithms we have. And we would discuss one of these algorithms in our hands-on coding session as well. So there are majorly 2 different kinds of algorithms or 2 categories onto how you can design your QML algorithms. The first is a variational quantum algorithm. Now, a variational quantum algorithm would consist of this particular set of unitary operations that have tunable parameters. That is, once you implement those set of unitary operations, they would have some kind of theta or parameters attached to them. And once you run this entire algorithm, you would evaluate what answers you get. You would evaluate the loss function. You would try to optimize it. And once you optimize this particular loss function that you have, you would go back to your algorithm, update those tunable unitary operations or tunable parameters, and run this entire algorithm again, and would keep on doing that until you get the appropriate parameters for, or the most optimized parameters for your algorithm. So these tunable operations, sorry, the variational quantum algorithms with these tunable operations are called parametrized quantum circuits. And by the name, it says quantum circuits that have tunable parameters. What you'll do is you will have data and you would encode that data using the data embedding techniques that we discussed. And once you have your data encoded, you would implement some quantum machine learning model. This model is this parametrized quantum circuit, with the meaning that it has certain trainable parameters. You would run these two things, data embedding and then quantum machine learning model, perform some measurements, get your expectation values or samples or counts, and you would evaluate this entire model. Once the evaluation and optimization is done, you would go back and update the trainable parameters with newer optimized values and run this entire algorithm again. So to give you more insight into how this quantum machine learning model looks like, this model would have certain unitary gates that have trainable parameters. So the parameters P1, P2, P3, P4, and P5, they may be trainable. That is, they can be changed. So you can imagine these gates to be some controlled RY gates with some different theta values, or RX gates with some different values. Okay, so these are variational quantum algorithms, data embedding followed by QML model with trainable parameters. You measure them, optimize them, and update the parameters. The next type of quantum machine learning model is a quantum kernel method. Kernel methods, they provide you, so kernel methods are these functions that provide you with a similarity measure between two different data features you have. And by similarity measure, I mean if you have two different features or two different data features, it would tell you how similar they are to each other. Let's say you have two apples, a green apple and a red apple. They have some similarity between them, although there is a difference in the color, but they still are categorized as apples. That is, at the end of the day, they're still apples. You wouldn't mind eating both of them. So you would have, you can use a kernel method to calculate the amount of similarity between them, how similar these two apples are to each other. And these kernel methods are built a little differently from how the variational quantum algorithms are built. So just to give you an insight, this is how the variational quantum algorithm looked like: data embedding followed by quantum machine learning model, measurement, and then evaluation and optimization. But a kernel method, on the other hand, it would take data and use some feature map to encode that data. And this feature map would also have some trainable parameters. So it would also contain your data encodings and trainable parameters, all entangled or stacked together. And then you would apply the inverse of this feature map such that it can give you a similarity measure. So you have a feature map and then the inverse of that feature map. And this whole thing is the quantum kernel that you're building. So the quantum kernel consists of feature map followed by the inverse of that particular feature map. And then you measure your quantum circuit. Again, evaluate and optimize the results that you get. Go back and update the trainable parameters in the feature map and the inverse feature map together. So the difference: in variational quantum algorithms, you have data embedding followed by quantum machine learning model, measurement, and then evaluation. But in a quantum kernel, you have feature map followed by the inverse of that feature map containing trainable parameters, measurement, and then evaluation and optimization. And in all of these, you go back, update the parameter, and run the algorithm again. I see a question. So for a task like, okay, the question is for a task like image classification, what is the most suitable type of encoding? Is there a one, or it depends on the data set? You're absolutely correct in saying that it highly depends on the data set that you're using and the purpose of encoding. You can use angle embedding, amplitude embedding, or the basis embedding for images as well. But since images can be huge, that is, the amount of pixels in these images can be huge, you will obviously go towards optimizing the number of qubits that you require in performing any embedding. So basis encoding would not be an optimal choice. So you may go for angle encoding or amplitude encoding for images. But the quantum image representation is also a research field in itself. And there are other encoding techniques that are particularly built for images, such as flexible representation of quantum images, multicolor representation of quantum images, and there are more entangled versions of all these methods that you can also use to encode the images. So all these methods, what they do is they optimize the number of qubits you would require to encode maximum number of pixels that you can have. And they also help you to encode color values. For example, images will not always be grayscale. They may also have red, green, and blue colors, or an RGB scale of colors. So you would also need to encode those color values. So instead of, let's say if you have a 2x2 image, which consists of 4 pixels, you would in fact have 12 pixels if you're trying to encode an RGB image, because it would have the red pixels, the blue pixels, and the green pixels. So the number of qubit requirements would also increase. So different encodings and the encoding you choose would then highly depend on the data set that you have and the problem that you're trying to solve. Awesome. So coming back to the presentation, we read about variational quantum algorithms, quantum kernel methods, and another, I would say, a subtype of quantum machine learning algorithm is a quantum neural network as well. So I would classify quantum neural networks as variational quantum algorithms too, because they also have sets of these unitary gates, or these sections with trainable parameters that you apply to the quantum circuit. At the end, you again optimize and evaluate, and then go back and update those trainable parameters or weights or the data set. So they are very similar to variational quantum algorithms, but their architecture can depend highly on what are the different things that you're trying to perform with those neural networks. Are you making an autoencoder? Are you making a generative adversarial network? Or are you, in this case, making a convolutional neural network with convolutional layers, pooling layers, fully connected layers, and finally the measurement? So the architecture is different, but overall, I would classify them as variational algorithms. Now, I know I've taken more time to explain this presentation, but quickly going on to the applications of QML so that we can start with the hands-on coding. Prominent application of quantum machine learning is to provide acceleration to the artificial intelligence and generative modeling models out there. So you can use quantum machine learning as a subroutine in a greater AI model or a machine learning model. That is, you can build quantum generative adversarial networks, you can build quantum convolutional neural networks, or you can also use something called these quantum tensor networks. That is just a combination of different unitary gates applied in a particular architecture so that you can accelerate what existing classical methods are out there. And you can use all of these methods in image classification, natural language processing, and any other application case that matches with the classical machine learning applications. The second, there are other applications such as in chemistry and material science. So you can, it's prominent to use generative models to find the ground state energy of molecules. One of the most prominent papers that I read is this one on generative quantum eigensolver, although it uses a classical generative model, but you can build certain Bayesian optimization techniques that help you figure out the parameters in these circuit samples or in the generative model, or you can simply use whatever architecture this paper right here tells you. You can also use quantum Boltzmann machine. They are also applied highly in chemistry and material science applications, for example, to find ground state energies. You can also use quantum machine learning in high energy physics and error correction. And for high energy physics, they're again prominently used for high dimensional modeling, how you can take particles or representation of particles from a lower dimensional space to a higher dimensional space, or this feature space, and then use kernel methods, quantum kernel methods, in either classifying them, clustering them. This particular architecture, it also uses an encoder and decoder, which means it could be an autoencoder or even a generative adversarial network that you can use to detect, to perform anomaly detection. And in other cases, you can use quantum machine learning models for noise modeling and adaptive error correction. That is, if you have some error on a quantum machine, you can use quantum machine learning models, or in fact, also simple classical machine learning models to correct or mitigate the errors that a quantum machine gives you or throws at you. Finally, there are a lot of applications, and I would say this is one of the most prominent fields right now, is optimization and game theory problems. So you can use quantum machine learning models for combinatorial optimization, in finance for portfolio optimization, supply chain optimization. And you can also use these algorithms like quantum Bayesian optimization to update the parameters in your quantum model. It's called hyperparameter optimization, and these are all prominent fields out there. The next thing on our slide is hands-on coding. I would take these questions and quickly move to the code. I would also share the GitHub link with you so that you can refer to those GitHub notebooks instead of writing the code with me. You can simply refer to those notebooks and try to run those notebooks as fast as you can, so that you don't have to waste time in looking at the screen and writing simultaneously. So I would quickly stop sharing here, share the GitHub link with you, take the question so that rest of you have time to go and clone that GitHub repository. Awesome. So give me a second here. Okay, so I am pasting the link to the GitHub repository. Meanwhile, I would take those questions. Oh, okay. So, Kitwin, thanks for sending the link. I would take the questions. So, the first question is, when should we use quantum kernels instead of variational quantum algorithms? A great question again. And I would say, again, it depends on the problem that you're trying to solve. So, if you're trying to run something like a quantum neural network, you can use variational quantum algorithms. Sorry, if you're trying to run something as a classical neural network, or you see that a neural network would be the best application for this particular problem, you can use a quantum variational algorithm in that stead. However, if you have certain problems where you wish to see how each data maps to every other data, that is, you want to see how the data is similar with every other data set, with every other data feature in the data set, you can use kernel methods. Kernel methods can also be used for classification, but mind that kernel methods require they have their own limitations and drawbacks. You would need to have a good or a well-suited feature map that gives you a good similarity measure. And you would also need to see the qubit requirements. You may have less qubit requirements when it comes to a variational quantum algorithm, but you may require more qubits when it comes to a kernel method. So it highly depends on the resources you have, the problem that you're trying to solve, and how the data set looks like. Some data set may also not be compatible with kernel methods. That is, it may be very difficult to find a well-suited feature map for your data. So in that case, you can go ahead and simply use a variational quantum method. And I would say another factor in this would be what is it exactly that you're trying to solve? Do you have a whole pipeline built out for kernel estimators? That is, do you have an algorithm that would process those kernels for you? For example, if you're using support vector machine, a support vector machine would want a kernel to be present. So you would use a kernel method there. But if you are simply using some neural network model, a kernel method may not be compatible with a neural network model. Okay, the next question is how to obtain the inverse feature map in quantum kernel method. Is it by reversing the order of quantum circuit? If that is so, do we need to use advanced techniques in the training process when computing gradients? Good question again. There are inbuilt methods in libraries like Qiskit and Penny that would give you the inverse feature map. And inverse feature map is you're absolutely correct. It is just the reverse order of the feature map. So let's say your feature map has a Hadamard gate followed by a C0 gate. The inverse feature map would have a C0 gate followed by a Hadamard gate. So it's exactly the reverse of your feature map. And you can simply use the inverse function in some of the libraries. And Qiskit also provides this inbuilt feature. You only have to provide the feature map. And if you're trying to build a kernel, it would automatically build the kernel for you. So you only need to provide the straight feature map to the kernel method in Qiskit. So everything would be done by the library itself. You would not have to write every circuit in its inverse form. Do we need to use advanced techniques in training process when computing gradients? No, there are no advanced techniques. You are either using loss functions like support vector classifiers to calculate what the loss is, or you're simply using optimizers like SVSA or Cobila or Adam in some cases to perform optimization. And everything is very user friendly now. So you would have APIs that would help you to, you would have abstractions to help you to do all of this stuff. What would be the advantage of using quantum machine learning model instead of traditional one to solve a problem? That is a good question. One advantage that I mentioned is that a quantum machine learning model or quantum computing, in fact, would naturally map things to a higher dimensional space. So it would require way less resources than a classical model would. And the another factor is it involves these quantum mechanical properties that can help you recognize a greater difference in the two data sets. Let's say if you're doing classification, it would help you map those two data sets in a very high dimensional space. Whereas if you try to do these higher dimensional mapping in classical, with the help of some classical models, such as classical support vector machines, they may require more resources and more computational power. So you would reduce the computational power by using quantum machine learning methods. However, if it comes to advantage, it is still not shown if a quantum machine learning model shows any advantage as compared to a classical machine learning model. So you can use hybrid methods to maybe use the best of both. Or try to use quantum as a subroutine or subtask in one of those classical methods. Awesome. If you do not have any more questions, let me quickly share my screen. Awesome. So I hope everyone has access to the GitHub repository. I would quickly show you the GitHub repository as well. Just give me a second. Sorry, I need to move this thing. There you go. Okay, so this is what the GitHub repository looks like. I already have a PDF of the presentation posted there. If you, however, if you go to this hands-on code directory, you would see there are a lot of different Jupyter notebooks here. I would be working with this workbook on variational quantum classifier here. It has some empty cells. So I would be completing this notebook and running the whole process for you. But if you simply want to sit and see how I'm in fact writing the code and how I'm running all the things, you can refer to this variational quantum classifier notebook. And in this notebook, you would see the entire code. I ran a sample code yesterday. So you would see every output of every cell that I'm going to run in the workbook. You would also see how I trained my model, the number of iterations I did, and the loss functions, the loss value that I got at the end, and how this is panning out, how good the model is or how bad it is. You can simply refer to this notebook while I complete the workbook side by side. Awesome. So let me quickly start with the notebook. I will, okay. So starting with these, now, oops, sorry. Okay, starting with this notebook, the first step is, of course, to um, import certain functions from certain libraries. And the most important functions or methods that we would be using, or the libraries that would be using, is NumPy, Matplotlib to plot how the data looks like, and Pandas for getting the data from certain CSV or Excel files. When it comes to Qiskit imports, we would be utilizing the quantum circuit and parameter values. We would also be using a ZZ feature map and real amplitudes. I would explain in a few minutes what the ZZ feature map and real amplitudes does, or I think we are not using ZZ amplitude, so we can remove this. And then we would be using Qiskit runtime estimators or primitives that help us to run our quantum machine learning model. But before we get started, the first step is to import data. Now, if you look in the GitHub directory that I shared with you, you would see in this hands-on code folder, I have this data set. It's called diabetes CSV and diabetes normalized CSV. So this diabetes CSV, it is a data set taken from Kaggle. I can share the link of this data set with you as well. So this data set classifies people on the basis of features such as their glucose level, their blood pressure level, if they are pregnant or not, the insulin level, BMI level. With these features, it tries to classify if the person is most likely to have diabetes or not. And so this data set has different feature values, but for correctly utilizing this data set, we need to normalize all the feature values so that we can have data. If you're using, let's say, angle encoding or amplitude embedding, the data must be between 0 to pi value or minus pi to pi values. So I've normalized this data set inside this diabetes normalized.csv file. And how I normalized it is using this normalized diabetes dataset Jupyter Notebook file. And this is how the file looks like. You can go ahead, run this file on your computer as well. And at the end, you would get this diabetes normalized CSV file. You can also, I've posted this notebook here so that you can see how I am normalizing the entire data set. Okay, so coming back to, okay, there is a problem here. I think I'll have to quickly, since I changed my laptop this morning, I will have to go and quickly update my Qiskit here. Give me a few minutes. Sorry about that. I had everything updated in my other laptop. Let me control notebook. I have the workbook here. Awesome. So hopefully this works. Oops. Okay. Yeah, there's a problem. Sorry, give me a few minutes to figure this stuff out. Okay, so I think I have a problem loading things here. Or maybe not. Okay, what I can do is I can quickly leave and rejoin through my other computer. I may have some camera problems on that, but I would hopefully be able to run this because I tested the file yesterday. So would it be fine if I take like 2 minutes to quickly run to my other laptop?
Yeah,
Awesome. Sorry
that's okay.
about this.
Thank you so much.
Awesome. Sorry about that. I am back and I can hopefully share my screen with you. I may not have my video on because I have some problems, but um, okay, sure. Okay, so here I have my workbook with me, and this would most probably run. This may be the latest update I have. Okay, it runs. So that is perfect. I hope you can all see the notebook. Awesome. So before we start anything, the first point, like I said, would be to import the data. So we have the diabetes normalized CSV. I would go ahead, run this thing. It uses pandas to read this CSV and then stores it into this data function. And I can see the data then. So I have different values, different features, such as if the person is pregnant, if they have what glucose level they have, blood pressure, skin thickness, insulin, BMI. There's something called a diabetes pedigree function. What is their age and the outcome? So -1 refers to no, they do not have diabetes, and 1 refers to yes, they have diabetes. The age, it looks something like this, which is not very common because, again, I have normalized the data set so that I can easily use it in any of the data embedding that I do. And along with importing this data, I would do a train test split that I would take this data and then I would split it into, first of all, I would make a data and a result section. That is, I would have labels separated. The outcome would be in a separate variable, and all the other data features would be in a separate variable. And then I would split this data into train and test set. So how I do that is I would, first of all, import this train test split from scikit-learn. The first thing that I would do is I would separate my data into data features and label. And how I would do that is I simply need to drop this column, so that, because outcome is my label, so I would store it in this y variable, and the rest of the data, since they're data features, I would store it in this x variable. So I'm simply dropping this outcome column and storing it as a label. And the number of features, I would need these number of features in order to perform data encoding and data embedding. These number of features would be equal to the number of features I would have here. If I count them, there are 8. 1, 2, 3, 4, 5, 6, 7, and age is 8. I would need 8 features. I can simply go and write 8, but the best way would be that I have this X data features that I'm going to get from this particular thing. And the shape of this X would be the number of features that I would have. And if I simply go and print the n features, you will see it is equal to 8. Now that I have my data and labels in X and Y, I would go ahead and split them in a ratio of 70:30, so that I have 70% of the data as my trained data, and 30% of the data I keep it separate so that I can test things on it. So I would use the train test split method from scikit-learn. I would call the X and Y, and I would mention the size of my test data set, which would be 0.3, 0.3, which simply means 30% of it. And then when I run this, you would see that 537 data points, they are in the X train. That is, I would perform training with 537 data points and testing with 231 data points. This next step is nothing but I'm simply changing my train the train set that I get here to an array. An array is more compatible with with the data embedding and the entire neural network classifier or the variational quantum classifier that I would be building with Qiskit. So an array is a compatible data type. Now, now it's time to go ahead and build the variational quantum classifier for binary classification. It's a binary classification problem because the outcome is binary. Yes, the person has diabetes, or no, the person does not have diabetes. Binary, yes and no. And how we do that is through multiple different steps. And these steps, I'm largely classifying these steps into 4 different parts: A, B, C, and D. The A part would be to build a variational quantum classifier algorithm. And this A part would include 2 steps. And these 2 steps include, first of all, performing data embedding. And second is building the parameterized quantum circuit. To show you in my slides here, oops, sorry, I think that doesn't work. Let me quickly turn on the PowerPoint and show that to you as well. So if you remember from the slides, building the quantum machine learning model or building the variational quantum classifier, it consists of 2 boxes. First is the data embedding, and followed by a quantum machine learning model. So this is exactly what we are going to do. We are going to embed the classical data. And what data do we have? We have these 8 different features for every person in the data set. We would embed these features, and then we would implement a parameterized quantum circuit, which is something like this here. We would build this parameterized quantum circuit. This is also called an ansatz. So we would build this ansatz with trainable parameters. So, and this is how we would build the variational quantum classifier algorithm. The next step would be to optimize the circuit and the operators. So we would set up Qiskit runtime service that would help us to run the circuit on Qiskit hardware. And the next step would be to transpile the circuit. So we may run this algorithm on various different backends, but this particular algorithm that we build needs to be compatible with those backends as well. That is, let's say we are only using 4 different qubits to build our algorithm, but this algorithm may have to run on a machine that has more than 100 different qubits. So we will have to transpile this circuit onto that quantum hardware using some transpilation techniques that I would also discuss. The third part is to execute the function, that is to run the function, get the results. And we would be setting up certain primitives for that help us to simply run the circuits that we have. And finally, post-processing, which is we would plot what results we get from running the entire variational quantum classifier circuit. Okay, so the first step is data embedding. I have provided a separate file that consists implementation of this angle embedding or angle encoding technique. If you go to the GitHub repository, you would see hands-on code, and hands-on code directory also has this utils.py file. This utils file is nothing but an implementation of angle embedding. You can go ahead and read this. It is very simple. I am only using RY gates to embed the data points. So the theta values of this RY gate would be the data features that I have, the 8 different features: glucose level, BMI, insulin, pregnancy. They would be used as thetas in this angle embedding for this RY angle. So you can go and refer to this utils file. But what I will do here is I would simply run this so that I can use angle embedding from the utils file in this Jupyter notebook. I would define how many feature parameters I have. So I would use a parameter vector. And this parameter vector would simply help me to define the different features given in my data set, and how many features do I want to plot onto a data embedding technique. And how many features do I have is equal to the number of features that I defined right here, 8. So I would use these 8 features to build a parameter vector of eight different parameters that I would be using in this angle embedding technique. So I would define embedding as angle embedding, use these end features, and also use the feature parameters. And then I would go and run this, and you would see that I have 8 qubits with RY gates on all these 8 qubits, and the theta values of these RY gates correspond to the data features that I have. 8 different data features: x0, x1, x2, x3, so on till x7. Now that I've completed data encoding, I would quickly go and look if there are any questions in the chat. Okay, there aren't questions in the chat right now. So let's come back. Now that I've done this data embedding part with the help of angle encoding, next step is to build this QML model. And how would I build this QML model is with the help of some parameterized quantum circuit. Now, Qiskit, the library that you're using, offers you inbuilt or backend built parameterized quantum circuits that you can use as ansatz or as quantum machine learning models in your variational quantum classifier. One of those ansatz is a real amplitude method. So this real amplitude method would have certain single qubit gates followed by 2 qubit gates that entangle all the qubits together. And I would be selecting this real amplitudes method as my ansatz. There wasn't any particular decision-making process behind choosing the real amplitudes implementation. It is one of the most prominently used implementations, so I simply picked it up from Qiskit. You can go ahead and explore other ansatz that are available. For example, you have real amplitudes, you have SU2 implementations, efficient SU2. You're free to choose them. And if you want to go a step further, you can build your own ansatz. You can define what single qubit gate or 2 qubit gates you need to see there. And you can build your own ansatz and also use that here. So for simplicity, I would define certain arguments here. How many repetitions do I wish to see and what my ansatz should look like. So if you see the ansatz looks something like this, you would have certain RY gates with some theta values and some 2 qubit entangling gates, that is the CX gate. Now, if you look carefully, the theta values here are theta 0, theta 1, theta 2, and these are different from the angle encoding that I did for my data features. So I'm representing my data features with the variable x and my trainable parameters with the variable theta. Now, the next step is to also keep a note of how many weight parameters do I have. And the weight parameters refer to all the trainable parameters that are present inside the ansatz. So any number of parameters that the ansatz would have would be my weight parameters. And if you look carefully, the last number here is 23, which means the ansatz has a total of 24 parameters. I can go ahead and print the length of this weight parameters as well, and you would see I have 24 parameters, and these would be called the weight parameters from now on. Now, I have the angle encoding done as my data embedding technique, and I have my ansatz here as a real amplitude ansatz. Now, looking back at this, I need to combine both of them in order to make my quantum machine learning model. So what I would do is I would build my final variational quantum classifier circuit. And how I would do that is simply by composing both of these angle embedding and ansatz together. So I would take my embedding circuit and I would compose it with the ansatz that I built. And this is a required argument here. That is the number of qubits that I'm combining together. It would be equal to the number of features that I define, which is I'm using 8 qubits. That would be 8. So if you see the final circuit, you would see The first layer of RY gates that you have here is the angle encoding, because the parameters here are the X parameters or the X data features. And the rest of the circuit you see is the ansatz, the real amplitude ansatz that we built. Now, the next part is to set up the circuit observables. Now, observables here refer to the measurement that you want to do at the end of the circuit. So at the end of the circuit, since this is a binary classification problem, I would like to only measure one qubit, such that that one qubit gives me an answer of is the person diabetic, or if the person is not diabetic. So I would only be measuring one. I would be measuring all the qubits, but I would be defining my observable measurement observable only on one qubit at the end. And how I would do that is I would take this sparse Pauli op function from Qiskit, which helps me define these observables. And how does the observable string look like is I would be performing an identity observable on the first 7 qubits, and then I would be measuring the 7th qubit or the 8th qubit in the Z basis. So I would not be taking any information from the first 7 qubits, but I would be taking the Z measurement information from my 8th qubit, the last qubit. So I would write I 7 times 7 and Z at the end. So it simply means that I'm measuring the last qubit, which is the 7th qubit, in a Z computational basis, or I'm measuring it in a Z basis. But the rest of the qubits, they would remain in their identity. I would simply measure them for the sake of measuring, but I would be getting my results from just the last qubit. You can try to change. So there is no hard and fast rule in having the Z observable on the last qubit. So you can build other observables with, let's say, Z in the first qubit, Z in the 5th qubit, Z in the 4th qubit. That is up to you. And if you want to do that very nicely, you can have Z on every different qubit, and then you can put all the results together to see what final result you get. But for simplicity purposes, I'll only keep my observable Z observable on the last qubit. Sparse Pauli op. Oh, sorry, it's not oop, it's op. There you go. Okay, so we have built a final variational quantum circuit, variational quantum classifier circuit, and we also have the observables here. The next step is to optimize this circuit based on the backend that we are going to choose. But in order to choose the backend, we need to set up this Qiskit runtime service. Now, Qiskit runtime service helps you connect your Jupyter notebook with the IBM Quantum platform and helps you get access to the available quantum hardware out there. And how you set up this Qiskit runtime services, you import the Qiskit runtime service module from Qiskit IBM runtime. And today I'm going to use the fake qubit backend, since I won't be basing my time on any real hardware available out there, but you can definitely go and try run it on the real hardware. I would, for simplicity purposes again, and for keeping time in mind, I would be using a fake qubit, a fake Quebec provider. This fake Quebec provider imitates what an actual IBM Quebec machine looks like. It is a 127 qubit machine. It imitates the qubit topology and qubit distribution, the error, everything on that IBM Quebec machine. So I'll simply call the fake provider module and get the fake Quebec class from there. So if you're setting up Qiskit runtime for the first time, you may want to uncomment these things. This would help you to save your account, such as define the channel that you're using, the token, the instance, and if there's a name for your project or something. There's a slight change. This channel IBM Quantum has now changed to IBM Cloud, I'm guessing. So you can make those changes, but I'm going to keep this commented because I've already defined my runtime service. I'll simply call it by calling the Qiskit runtime service thing and defining my instance, which would be similar to yours, IBM Q open main. And I would define a fake backend, which is the fake Quebec backend. But if you want to try the entire code on a real IBM Quantum hardware, you can uncomment this line, which tries to get the least busy hardware out there for you. It would not be a simulator because simulator is false. So it would try to get the least busy hardware out there. So I would run this cell. I would have my fake backend. And once I have set up my Qiskit runtime service, I would go and perform transpilation on my circuit, the variational quantum classifier circuit. Now, as I explained before, transpilation means you are modifying your existing circuit, the circuit of 8 qubits that we made. You're modifying it in such a way that it is compatible with the hardware that you're going to run it on. In our case, since I'm going to run it on a fake Quebec backend, the fake Quebec backend mimics the IBM Quebec machine. So the transpilation methods here would modify my circuit such that it runs or is compatible with the IBM Quebec machine. And how I would do that is using preset pass manager. So preset pass managers are a module of transpilation passes that Qiskit defines for you. So these are all inbuilt. I will only have to call this generate preset pass manager. This would perform all the transpilation for me. I would only have to call it. And how do I call it is I define my pass manager as generate preset pass manager, and I provide certain arguments here. I would first of all mention my backend, which is the fake backend that I'm using, the fake Quebec machine, and the optimization level. So these are required arguments. So I will have to mention everything. Optimization level, it optimizes the amount of transpilation that you are doing with your circuit. I'm keeping it to 1 for simplicity purposes, but you can change the optimization level to make your circuit more optimized and compatible for the backend. Now, if you want to see how the transpile circuit looks, you can uncomment these 2 lines, and I will run them and show you how the transpile circuit would look. It would have all the gates that we added onto our variational quantum classifier circuit, but they would be decomposed into basis gates that are compatible with our backend. So there you go. So you see, we are using the same RY gates, but the RY gate is now decomposed into the square root X and the RZ gate, that these basis gates are compatible with the IBM Quebec machine. So this is the transpiled version of our variational quantum classifier circuit. We'll go ahead and come to the point of mapping observables, come to this cell right here. Now that we have transpiled this 8-qubit circuit onto 100 plus IBM Quebec machine, there also needs to be mapping of the observables. So the IIIZ observables that we defined before, they also need to be mapped to a 127 qubit machine. So how we do that is I would apply the same layout as I did to my variational quantum classifier circuit. I would take the layout of this variational quantum classifier transpile circuit, and I will apply this layout to my observables. So if I run this cell, you would see this is what my observable string would look like. It would have 126 numbers of eyes and then the last qubit z would be the last qubit would be the z observable, because this is where I'm performing my measurement. And they are all, remember, Qiskit always reads things in the opposite direction, so you would assume this is how I'm defining my observables. Now that we have mapped the observables, transpiled our circuit, the final step is to execute and get the results. For execution, first of all, let's do the imports. I would require certain use of estimator quantum neural network to define the workflow of how I'm going to run the variational quantum classifier. Estimator quantum neural network would help me get expectation values at the end of my circuit. That is, if you see here, the measurement results that I would get by using the estimator QNN would be expectation values that I would log into certain loss and optimizer functions and then bring them to update the parameters. So I'm using an estimator QNN. Your option can also be to use a sampler QNN, which instead of providing you with expectation values, gives you the number of counts, that is the number of samples, the number of times you would receive. Yes, it's a diabetic person. No, it's not a diabetic person. And you can also use sampler to update your parameters. But here I'm going to use the estimator. I would also call a neural network classifier. I'll feed my circuit into this neural network classifier such that it works as, or it runs as a classifier problem, a classification problem, and then provide me with the results. Now, all of these things, both of these things, the estimator QNN and neural network classifier, they are wrappers around how classification is done with Qiskit. And the next thing would be to call an estimator, because since I'm running an estimator QNN, I would require expectation values at the end of my measurement. I would call this estimator primitive to provide me with those expectation values. If I want the number of counts, I would be calling a sampler. But if I want expectation values, I would be calling an estimator. And finally, the optimizer that I'll be using here is a Kabbalah optimizer. This is just a wrapper for the classical Kabbalah method. You can go and read more about this. Google has a lot of resources to know what different optimizers you can use. Now let me define this primitive right here. Now, since I mentioned I'll be using this estimator primitive, I'm going to define the estimator here. To explain more on what this estimator does is, it takes the backend that you're going to use and it makes sure it connects you to that backend and you run your things on that backend. So it's just a primitive function. And primitives is something that Qiskit defines as modules that connect you to the backend or the simulators that are in the IBM environments. So they're just a method of providing your circuit to them and running it on the back end. But they govern what measurement results you get at the end. You either are getting an estimate, with using estimator, you're either getting expectation values, or by using sampler, you're getting counts or the samples out of a sampler. Then I'll go ahead and define my quantum neural network primitive. Now, your question would be, if you're building a variational quantum classifier, why are we using a quantum neural network primitive? And the simple answer is, this is how Qiskit defines things. So the quantum neural network method is nothing but a method, a class that takes in all your circuit variables, parameters, and runs it assuming it's a neural network or a variational circuit. And as I mentioned, neural networks are also a type of variational quantum algorithm. So this is simply how Qiskit is defining things. It's assuming that you're doing the data embedding, you're building a parametrized quantum circuit or an ansatz after it, and then it would simply go ahead and run it as if you're training a neural network model or training a variational model. It's just this estimator QNN is just the name of a module. What I would provide to this estimator QNN is the estimator that I have, estimator that I defined right here. The circuit is going to be the variational quantum classifier circuit that we defined right at the beginning, not the transpile circuit, because it would do the transpilation itself. We don't have to provide transpilation to it, or actually we can also go ahead and provide it with the transpilation, but I think the estimator QNN handles the transpilation itself. But we would be providing estimator QNN with this variational quantum classifier circuit, this circuit right here that we built. Okay, the observables are the mapped observables. This string of 127 alphabets, mapped observables. Input parameters are the feature parameters that we defined, or the feature parameters, these 8 parameters that are input as features, or the data parameters. So we would put in those feature parameters here. The weight parameters are something that we defined here. There you go. These 24 weight parameters in the ansatz, these are considered as a weight parameters. So we would also pass those. And finally, it asks for the pass manager to perform transpilation. So since I'm only providing the variational quantum circuit here, the pass manager, it is the pass manager's job to take this circuit, transpile it, and then use the transpiled circuit to run it on the fake Quebec backend. So where I define the pass manager is right here. So my pass manager is generate preset pass manager. And I would go ahead and run this cell. Estimator, oh, sorry, I did not run the imports. Wait, params. There you go. Sorry, I'll just take a minute off. Awesome. If you have any questions, feel free to ask. Okay, so the next step is to, now that we have defined our estimator QNN, what this primitive is doing is it's bringing in all the parameters, all the circuits, transpilation methods all together and wrapping them up so that you can now send it on to a neural network classifier method to run the circuit. And the neural network classifier is this method right here. It would take everything in so that you can finally go ahead and run the entire circuit in a loop method. That is, you would run, get the optimization loss values, update the parameters, go back, build the circuit again, get the expectation values or the optimizer values again, update the parameters, the theta values again, and keep on doing this until you reach the maximum number of iterations. So for this neural network classifier, what we need to give to this neural network classifier is the neural network that we built. And the neural network is, again, just the name. It is confusing, I agree, but it is just the name of the argument that Qiskit defines. So the neural network that we defined here is this estimator QNN. I would simply go ahead, copy this and paste it here because this estimator QNN has all the information about the variational quantum classifier that I'm going to run. So this would be considered as my neural network, and I would be passing this information here. The optimizer that I'm going to use is the Kabila optimizer, as I mentioned, and the max iterations that I'm going to do here, keeping in mind that I would only be running 30 iterations, but you can increase these iterations to as much as you want. You can perform 100, 200. The more number of iterations, the better the classification you would get. And then I would pass this callback argument. Now this callback argument is nothing but a small callback graph. And what this callback graph does is it would keep on noting the loss values that I get from this Covilla optimizer, and it would continuously keep on plotting uh, the training for me. So every iteration that I do, it would plot the loss value on a graph for me. Now, if you don't want to build this callback graph yourself, I have it here. I've taken some things from Qiskit and I've added few things of my own. So this is a pre-made callback function for you. I simply need to go and run this cell, and then I can pass this callback graph in my variational quantum classifier thing here. I would go and run this. Now I have my variational quantum classifier all ready, the entire workflow ready. That is, it has the neural network or the variational quantum classifier circuit, the number of features, feature values, and the entire workflow setup. That is, it is going to run with a Covilla optimizer, and these many iterations, it would run for like 30 iterations. Now, the next step is to define this objective function value. It's an empty list. It would just store every loss value that I would get by running this Covilla function. And I would then go ahead and fit my variational quantum classifier to the trained data set that I have. So I would fit it to the X train, which is the data features, and Y train, which are the labels. And I would run this cell. Now, this cell would take some time to complete because it would run up till 30 iterations, and it would simultaneously show you a graph of how the training is being done. It would take some time to complete. Hopefully, it gets it done. It gets done on time. Meanwhile, I'll take questions. Okay, we have one question here. If it's real quantum hardware, then it would not take any time to train. It would take time to train because real hardware also needs to run all of the workflow. It would run on the hardware. It would go back, optimize, run that again. If you're talking about how much time it takes on the machine, it may take less time, but there are other certain factors that define the total time for running your algorithm. And the total time includes the time you are in the queue to get access to a particular hardware, the time it takes for the optimizer to run its functions, give you a loss value, and go back and build a new circuit. It would definitely take less time to run just the circuit on the quantum computer, but including the other methods, that is the optimization or the time you spend in queue for accessing the quantum hardware, would also be included. So you will definitely see more time being taken to run the entire program. Now, coming back to this, we ran vqc.fit on our X train and Y train. And here is the graph that we see. So it calculates the objective function value, that is the loss function value that you see right here. So it would plot these loss values at every iteration. And this is simply the number of iterations. So now we know it has, we have only run 5 iterations until now. Until it runs 30 iterations, we'll see this graph being built. It would take about 5 minutes to run, 5 to 10 minutes to run all the iterations. I could have reduced it to just 20 iterations, but it's okay. We'll see 30 iterations. I'll take questions meanwhile. So you can see that the objective function value, or the loss, was huge, but now it is reducing as the number of iterations increase. So reducing the function value, that is the cost function, or the loss values, and reducing it to a minimal value is what we expect. So we only have run 10 iterations. We have 20 more to go. So once we have our variational quantum classifier trained, we would go and then we would go ahead and try to get the score of the variational quantum classifier. And the score is how nicely has it predicted the labels in the X trained data set and the X test data set. Although the train scores are not very important, we would only need the test score because we are verifying it with the test. Like if we run our trained variational quantum classifier on X test, what is the score that we get? It would give us prediction values and compare those predicted values with the actual Y test values and provide us with a score. 15 done, 15 more to go. It would just take 3 to 4 more minutes to see the function value reducing or the loss value coming down. The more iterations you run, you'll see a better graph. You can also see that in the GitHub file, the thing that I've already trained. If I go back here, variational quantum classifier, you would see this objective graph here. I ran it for 60 iterations, and you can see that it increased for a while, but then it consistently reduced and was minimal. It was something below zero point 0.7. The at 60th epoch or at 60th iteration, it was the function value was 0.67, and this is at least this is what we'll try to get at 30 iterations. So it's at 18 iterations, 12 more to go. Okay, I see some questions here. Are there any quantum computing or quantum machine learning related courses or certifications we could take? That's a very good question. I think all the material that is available is either online on YouTube or in books. There has been a little lack in the quantum machine learning resources out there. I haven't really come across a good resource. This is unfortunate and not a good thing on my end as well. But there are less resources online. There isn't a particular resource that I would recommend. So you either read certain papers or some starter papers or white papers that introduce you to the scene in quantum machine learning. That is, you could see survey on quantum machine learning, white paper on quantum machine learning. Such papers would give you a better insight into what is happening. And the rest of the resources that you have is to refer to the code books and the demos that different companies provide you. So you can see Qiskit, the older versions of Qiskit textbook, if those are still available, or you can go and check Penny Lane demos. They give you a very nice insight into what is happening. If I ever come across any good resource, I'll definitely share it with the professor or Kitman, and you can get in touch with them to get those resources. What is the loss function here? Is it the average error? How is it greater than 1 first? That's a good question. I actually never saw what the loss function is by default in a neural network classifier. Let me quickly check. I was assuming it would be a minimum squared error. So if it's a minimum squared error, it would be square of the loss that you would get. and it can be greater than 1. But let me confirm this. Neural network classifier. Yeah, that is correct. It is the squared error. So I'm using this neural network classifier method, and the loss by default is the squared error. So it would be the mean squared error if I'm not wrong. Or maybe it's not the mean squared error, it's just the squared error. That is why it is greater than 1. Uh, so it is loss, a target loss function to be used in the training. By default, it's the squared error, that is the L2 loss. And it can also be an absolute error, which is L1 loss, squared error, cross entropy, or a loss function implementing the loss interface, that is some function that you can define by yourself. But by default, since I'm not defining anything, by default, it's the squared error. Okay, I think I missed a question here. What operations are done on quantum computer and what are done on classical GPUs? You said that data exchange between quantum and classical states is the main bottleneck, and that rather hinders the computational advantage we get by running these algorithms in quantum computers. That is absolutely correct. So, looking back at this presentation right here, the things run on a quantum computer is only the data embedding and the quantum machine learning model that you use. So you would have data embedding circuit, quantum machine learning model circuit, or the ansatz, and this is the only thing that you're running on a quantum computer. The rest of the evaluation and optimization, that is the things done right here in this thing, the optimizing calculating the loss function and then optimizing the loss function and getting these values. Each and every of this thing is done on a CPU. The only thing performed on a QPU or a quantum machine is this running the data embedding and running the quantum machine learning model. That is it. And it is absolutely correct to say that this data embedding part is the main bottleneck that, as you said, hinders the computational advantage. I would say it hinders the entire workflow of a quantum machine learning model because data embedding introduces a lot of complexity and a lot of entanglement, a lot of gates. So the more number of gates, qubits, or entanglement that you have, the more resources it would require for you to run this entire circuit. And this would also introduce a lot of noise, a lot of time to execute your circuit. If and certain data embedding techniques are simply not optimized to perform well on every data set. So most simply, we're running an angle encoding here. The angle encoding uses 8 qubits to encode 8 data features that we had. So we had these 8 data features, pregnancies, glucose, blood pressure, skin thickness, and stuff. 8 features, and we're using 8 qubits. But what if you're running an image, let's say a 10 by 10 image? A 10 by 10 image is extremely small, but since it has 100 pixels, because it's a 10 by 10 image, and if you're trying to use angle embedding with it, you would have to use 100 qubits to encode just a single image. And that is not an efficient resource or an efficient encoding because it requires 100 qubits on your end. And the maximum number of qubits that we have may be just 150 or 160. So that explains how and why data encoding or data embedding methods are the main bottleneck in quantum machine learning right now. Okay, I think we completed 30 bucks, which is great. 30 iterations done. The loss at the end of 30 iterations is 0.9. Not very good, but also because we only ran 30 iterations. We may have to run more in order to reduce this loss by more, but this is how our objective function value looks like. Now we'll go ahead and calculate the score on the test set. Now we'll test it with the test set to see how our variational quantum classifier is performing. I do not expect a score greater than 75% or 70%, uh, because we ran it on 8 qubits, which is huge, but we also ran the entire circuit for only 30 iterations. We are not, as I said, it is 65.8%. So that is our score on the test set, or accuracy on the test set. Um, but it's just for depiction purposes. There are a lot of different resources, a lot of different methods that you can use. And it would be a great research area for you to see how you can improve the accuracy on the test set here. You could have data set, sorry, data set consisting of larger number of data points, or you could have a better data embedding technique that uses less than 8 qubits. You could train it for more number of iterations, and you can train the entire variational quantum classifier on a larger data set, maybe like 10,000 data points or 20,000 data points. Now that we have completed the training, we have the scores. The next part is to simply visualize how things are doing. How I'm going to visualize this is, first of all, I'm going to uh, collect all the predicted points. So I'm running my variational quantum classifier on my X test data set and predicting all the labels. Then I'm going to compare these predicted labels with the actual labels that I had in my data set. I would build um, a collection of those. And then I would use this scatter plot to see how many misclassifications do I get, how many data points were correctly implemented, and how many do I have to implement. Sorry, how were rightly classified and how many are misclassified. Okay, pair plot data is not defined. Okay, sorry, give me a quick second. Oops, I would actually hold on. I need to check what is wrong. Pair plot data. Oh, okay. Maybe I'm not defining it correctly. So let me go back here. Okay, this is data. I'm going to copy this. Pair plot data is equal to data dot copy. There we go. I'm going to run this. Okay, just a second. Okay, I'll have to see how this needs to be done. It is not taking. Since I split this here, it's not. Okay, so I would quickly switch back to my older file because I need to figure this thing out. But if I go to my older file, you would see, okay, this is somehow that I'm something, this is something that I'm not running here. which is a problem. I would update this. I need to add in a few more lines of code to make sure that the pair plot data is it contains all the X test data set that I'm using. So I would run this. I would create this pair plot data values. And if I would go and plot these pair plot data values with the help of my scatter plot. And this scatter plot is a two-dimensional plot. So it would only compare two features at a time. So I am handpicking those two features, no particular decision made behind it. I'm taking glucose and blood pressure levels, and I'm comparing how many correct classifications and how many misclassifications did my variational quantum classifier make. And this is what the entire this is what the entire graph looks like. So it compares glucose with blood pressure, where glucose is I think one of them, the glucose is classified as the purple dots, and the blood pressure is classified as the yellow dots. And they, oh no, sorry, sorry, the glucose is on the x-axis and the blood pressure is on the y-axis. Purple means that this person is most likely not to have diabetes, because purple means an output of -1, and yellow means an output of 1, indicating that the person would most likely have diabetes. And all the misclassified people are marked in these red cross. So every cross that we see is the person who was misclassified. So some of them were classified to have diabetes, but they would not have diabetes. Although they do have an okayish glucose, but a high blood pressure, they would still not have diabetes. But there were also certain people classified to not have diabetes by being in purple, since they have less glucose and almost negligible blood pressure, but it turns out that they did in fact have diabetes. So you can see almost 40% of these labels are misclassified, since our variational quantum classifier could only work on 65%. Sorry, in this case, since I ran it for 60 iterations, the score was 73%. So you can see almost 30% of them being misclassified. You would see more misclassifications if you run this file right here. Although there are a few things missing in this file. So I would go back, add some lines of code, and then update it on the GitHub as well for you. But overall, not a bad result. And this is how you can hands-on run a variational quantum classifier and use Qiskit in training this variational quantum classifier and building a quantum machine learning model for yourself. This is it from my end. Thanks for joining. And you can always reach out to me. These are my two email IDs. Sasha.joshi@cmc.ca and sashajoshi0@gmail.com. You can reach out to me anytime you feel like. If you have any questions regarding the presentation or the hands-on code, you can let me know.
Yeah, thank you very much, Shahsha, for the actually very informative, detailed session on the. In fact, it started with the classical machine learning and also then moving into the quantum and algorithms and finally the hands-on session. And if there are any other questions from the audience, you can ask from Shasha now.
Thank you so much for calling me here. It was a very nice session, and I really loved all the questions that everyone asked. Okay, my camera
Yeah.
works finally. Sorry,
Yeah.
it has a very dim lighting, but it works.
Yeah. So if you have any question, you can ask directly, or basically you may let us know in the chat. I know that already you have asked quite a lot,
Yeah,
questions,
feel free to
and
ask any questions. Um,
yeah,
if you cannot ask questions right now, you can always email me. You can note my email IDs down. They're also in the
yeah, we will
PDF.
share. Yeah, yeah. Basically, Kitmin, and I have also your ideas, and if someone wants to actually get some feedback or some guidance from you, we will share, and we really appreciate actually that.
Yeah, no worries. I had
Um,
a lot of fun.
yeah.
I do see one
Uh,
question here. So, during optimization of neural networks, does Hamiltonian play any role? That's a good question. So, it it depends. Uh, Mostly Hamiltonians are defined when you are defining the cost functions. So the cost function of, let's say, a two molecule, or in quantum chemistry, a two molecule set would be defined as a cost function, because that is when you're trying to get the energy, or the ground state energy, or the bond length between any two molecules that you have. So you would define your cost function as a Hamiltonian. But in quantum machine learning, you're defining your cost function as the quantum machine learning model that you're building, the one that consists of the data embedding and the ansatz, or the parameterized quantum circuit. So there isn't any Hamiltonian in play here. You can, if you still see cases where Hamiltonians are, so cost functions would not be called Hamiltonians in quantum machine learning, but sometimes you do get to see these things when you're defining the observables. That is, which observable and how do you want it to be defined as at the end. So we took the IIIZ thing. You may also see the coefficients of those Hamiltonians, and those Hamiltonians playing a role in defining those observables in certain cases. But it would be only in particular cases when you're dealing with a particular kind of a data set. In any other case, there's not a particular Hamiltonian, it's only the cost function that you're building.
any further questions? Okay, so it looks like there are no more questions. So uh, we may conclude the session. I would like to thank again Shasha for accepting our invitation and presenting a very detailed, informative, and yeah,
Thank you
enlightening
so much
session.
for
I
that.
also learned new things, and thank you so much. And so the if you have anything to get from Shasha through emails, let me know, get me know, and we will make the connection between Shasha and the some students for to do. Then we'll conclude, and so thank you very much, Shasha, again, and
Thank you so
good
much.
night to everyone in Sri Lanka, and good day to Shasha and
Thank you
Teshani
so
also.
much.
Yeah, a good day.
You
Yeah.
were a great audience,
Okay.
everyone.
Okay.
All
Thank
the
you so
best.
much.
Bye
Okay.
bye.
Thank you. Okay. Right. Bye.